elevation in boiling point. This we represent with the symbol delta TB. So, if TB naught is boiling point of a pure solvent, TB is boiling point of solution, then as already we told, TB is greater than TB naught and TB minus TB naught, that is equal to delta TB, is what is called elevation in boiling point. Now, graphically the pressure, vapor pressure and temperature graphs if you draw, pressure versus temperature, when we draw a graph. In the concept of vapor pressure, already we told that with increase in temperature, vapor pressure increases. This is the borderline of atmospheric pressure. For any liquid, the maximum vapor pressure is the atmospheric pressure. So, this is a saturated vapor pressure. This now if you extrapolate, then at this is atmospheric pressure. This first curve is for pure solvent, second curve is for solution 1, solution 2, where in this the concentration of solute in solution 1 is less than concentration of solute in the solution 2. This is pure solvent, less concentrated solution, more concentrated solution. Now, the corresponding temperatures, this is the atmosphere, this is the temperature, I will represent it as T naught, or rather more precisely I will put it as TB naught, that is the boiling point of the pure solvent. The reason being that this is the temperature at which vapor pressure of this pure solvent is becoming equal to atmospheric pressure. So, this temperature is the boiling point of the pure solvent. Now, this is, I will put it as TB dash. TB dash is now indicates the second curve is for solution 1, or rather lower concentrated solution, for which this temperature indicates the boiling point. So, this is the boiling point of lower concentrated solution and this is TB double dash. The TB double dash is the boiling point of the solution 2, that is more concentrated solution. Now, if you compare these three from the figure, you can easily say that TB double dash is greater than TB dash is greater than TB naught. That means boiling point of more concentrated solution is greater than boiling point of the lesser concentrated solution than the boiling point of the pure solvent, right. Now, this TB naught, TB dash minus TB naught, this is the delta TB dash, that is the elevation in boiling point for solution 1. TB double dash minus TB naught is the elevation in boiling point for more concentrated solution. Now, these elevation in boiling points delta TB and delta TB dash and delta TB double dash, these two, how they relates to concentration is what now we can see. Now in this, if you look at it, this corresponding pressures, if you look at it, this is P naught, this is P dash, and this is P double dash, right? This is for pure solvent, this is for solution 2, this is for solution 1. So as you can see in these cases, now if you take the triangles like this, if you note it down as A, B, C, this is D and E, F, like this, if you note it down the points of intersections. In the graph, once again if you look at it, that the pure solvent, solution 1, solution 2, when the curves have been drawn, from the graph the ratio of AB to AC, considering that this 2 will form the two identical triangles, AB by AC will obviously be equal to AD by AE, the two identical triangles, like if you look at it, which is nothing but, now AB is nothing but TB dash minus TB naught, TB dash minus TB naught, and AC TB double dash minus TB naught. That is what we are writing here. And on the other side, y axis, if you look at it, AD by AE is nothing but P naught minus P dash divided by P naught minus P double dash. So that means elevation in boiling point in solution 1 divided by elevation in boiling point of solution 2 is equal to decrease in vapor pressure of solution 1 divided by decrease in vapor pressure of the solution, the change in vapor pressure of solution 1 by change in vapor pressure of solution 2. So that means delta TB dash is directly proportional to delta P dash, delta TB double dash is directly proportional to delta P double dash. So in general, we can say that the elevation in boiling point is directly proportional to the change in vapor pressure. In case of a nano solution containing non-volatile solute, the vapor pressure increases. So increase in vapor pressure increases boiling point. This is what we say elevation in boiling point. So the statement now we can give it like that: to a solution, to a pure solvent, when a non-volatile solute is added, not only that its vapor pressure increases, but also its boiling point increases, right? Now this I will write it as delta TB dash by delta TB double dash. This I will write it as delta P dash by P naught into P naught by delta P double dash. It is like multiplying and dividing it with same quantity, that is P naught by P naught, right? Now delta P dash by P naught is nothing but relative lowering of vapor pressure of solution, which is equal to mole fraction. Similarly, P naught by delta P double dash is nothing but inverse of relative lowering of vapor pressure of the solution 2, right? So these two is now I can write it as that delta TB dash by delta TB double dash is equal to, this is relative lowering of vapor pressure of solution 1, which I will write it as mole fraction of solute in solution 1 by mole fraction of solute in solution 2. Now this is in fact is nothing but the mole fraction of solute in solution 1, mole fraction of solute in the solution 2. Mole fraction and molality, mole fraction and molality are again directly related. So also I can write is that it is equal to molality of solution 1 by molality of solution 2. Therefore delta TB also I will write it as directly proportional to molality of solution. when a non-volatile solute is added to a pure solvent to form a solution, the elevation in boiling point will be directly proportional to molality of the solute in solution, right. Now, this is about the how elevation in boiling point is related to molality. Now, equation for this we write it. Now, we write it as delta Tb is equal to Kb into molality, where Kb is the proportionality constant for the in equation. This proportionality constant Kb is defined as or is called as molal elevation constant or ebuloscopic constant. Now, we discuss what is this Kb in detail. Now, delta Tb is equal to Kb into molality is what we wrote, where Kb is what we are calling it as molal elevation constant, or it is also called ebuloscopic constant, which can be defined as that it is nothing but Kb can be defined as that elevation in boiling point for a solution of unit molal. Unit molal means this Kb is nothing but elevation in boiling point of a solution when molality is 1. When molality is 1, what? Delta Tb is equal to Kb. So, this is nothing but elevation in boiling point for a solution of unit molal. So, the unit for Kb is Kelvin kg per mole. This is the unit. Kb is equal to RTB square by 1000 LV, where LV is latent heat of vaporization. R is gas constant, Tb is the boiling point of pure solvent. Tb is the boiling point of the pure solvent, LV is the what? Latent heat of vaporization, R is of course gas constant, right. The same thing also we can write it as RTB square into m by 1000 delta HV. What is delta HV? Delta HV is nothing but enthalpy of vaporization. LV is the latent heat of vaporization, delta HV is the enthalpy of vaporization. What is the difference between both? LV is for per gram heat required to evaporate 1 gram of a substance. Enthalpy of vaporization is heat required to vaporize 1 mole of a substance. So, delta HV is equal to LV into m, that is actually the relation. So, we write it as RTB square into m by 1000 delta HV. This is how we define Kb. And for pure water as a solvent, this Kb is equal to 0.52 Kelvin kg per mole. This is the one most frequently what we come across in solutions. So, Kb is equal to 0.52 Kelvin kg per mole. Now, this is the actual concept of elevation in boiling point. What is the use of this elevation in boiling point? Where do we specifically use? This is a very basic principle that what we use in pressure cookers. As you know that in pressure cooker the cooking time is definitely less than you cooking the same amount of food in normal classical vessel. In pressure cooker the time is less. What is the reason? Immediately what we expect, the answer what we get is that in the pressure cooker the temperature, the boiling point of water is decreased. So, water easily boils and the cooking time is reduced, but that is not correct. It is not that boiling point of water is decreased, it is boiling point of water is increased. Why? What happens? The method, the principle, the actual thing what is involved in pressure cooker is that we take some amount of water in the cooker, then of course the food item will be kept in a vessel inside it, then it is closed tightly, airtight close, we do it, then it is heated. When it is airtight closed, then what we are doing is we are increasing the pressure inside. That is the reason, in fact, we call it as pressure cooker. When the pressure inside is increased, means the temperature to which the vapor pressure of that liquid, that is pure water what we are using in the cooker, to reach to that increased pressure, because that whatever the pressure inside the cooker is not nothing but like atmospheric pressure, that is the external pressure. So, the water in the cooker, if it reaches to that particular temperature, then actual boiling starts. So, as a result what happened now, the water in the cooker will require more temperature to reach that increased pressure. So, as a result what happens, as it requires more temperature to heat it to a high temperature, what you are supplying is more heat. When you are supplying more heat, that increased quantity of heat is available for the food to cook in that. So, as a result finally what you are doing is, in brief, by increasing the pressure in the pressure cooker, you are elevating the boiling point of water. As a result more heat is supplied. As more heat is supplied, the cooking time is reduced. This is a basic simple principle in the pressure cooker where the cooking time is reduced. That is the reason, in fact, always we advise everyone to use pressure cooker so that your fuel consumption is minimized as well as cooking time is reduced and valuable vitamins will not evaporate as everything is tightly closed and inside. So, this is what is the basic principle is increase in pressure increases the boiling point. Advantages, of course, other than this what we have is the other things as what we told. So, this is a simple direct application of elevation in boiling point in a solution compared to that of pure solvent. And the same principles even how a cooking time, whether it is reduced, increased or decreased when we go to higher altitudes. In every case it is the same. As the pressure increases, cooking time reduces. As the pressure decreases, cooking time increases, or food cannot be cooked. At higher altitudes we cannot cook the food. The rice cannot be cooked. The reason exactly opposite to this. So, this is how the general applications of this elevation and boiling point is what we can discuss in this case. Now, after this we go for depression in freezing point.